Okay, so here we shall consider one of the basic rational function 1 over x, and this function has a unique name, reciprocal function. So here we will try to sketch the graph of this function by considering few key points. And before sketching the graph of the function, we first need to know the domain of the function, and then we need to cover the range of the function, and these are the pre-basics before sketching the graph of the function. So as we can see that in this rational function 1 over x, we have a precondition that x cannot be equal to 0. So what we can say from here, that the domain of this function can take up any real values ranging from minus infinity to infinity. Obviously they are not included except 0. 0 cannot be in the domain of the function. We cannot include 0 in the domain of the function, because at x equals to 0 the function is not defined. So the domain of this function is the set of all real values r excluding 0 from that set of values. Now this is one of the form by which we can write the domain of this function, and also if we let it be the origin, this is the origin, and this is our y-axis, and this is our x-axis. So this is the positive x-axis, and this is the this portion is our positive x-axis, and this portion is our negative x-axis. So we can write the domain of this function in the expanded form too. Domain of this function can be rewritten as minus infinity, because actually this is approaching towards minus infinity x if we go from the left hand side of the x-axis, minus infinity to 0, union 0 to infinity. So this is the expanded format while writing the domain of the function, and this will give us the endpoints of the domain, because we need to know the endpoints of the domain. We need to locate the endpoints of the domain. These are the 4 endpoints: minus infinity, 0, 0, and infinity. So this will give us a better picture of the domain of the function. Now we will try to find the range of this function. Now range of this function, somehow we could say that range and domain are interlinked. Suppose if we write like this, let y, that is our fx, is equals to 1 over x, and we have a precondition that x cannot be equal to 0. Now we are writing like this, we are expressing x in terms of y, that implies x equals to 1 over y. Okay, so let this be another function, say gy. Now we shall try to find the domain of this function gy, and this will give us the range of our original function. Now as we have seen before, that the domain of this function is a set of all real values excluding 0, so we can say the domain of this function gy is the set of all real values except 0. That means this function can take up any possible real values except 0. So this will ultimately give the range of this function. So range of this function is the set of all real values excluding 0. Okay, so this gives me the domain and range of this function. Now we shall consider few more points to draw the graph of this function. Okay, let me rub this part. We have already concluded what is the domain and range of this function. Now we shall try to highlight some other points before sketching the graph. Okay. Let me rub this first. Okay. Now here we can see that by the consistency rules of mathematics we can say that division by 0 is not allowed, so x cannot be equal to 0. X cannot be equal to 0. Therefore we can say at x equals to 0, at x equals to 0, we have a vertical asymptote. We have a vertical asymptote at x equals to 0, and that is y-axis. So this y-axis is our vertical asymptote, and we must remember that vertical asymptotes or horizontal asymptotes share lines, because x equals to a number, y equals to a number represents a line. So we can mark this with some dotted line like this, and this is our vertical asymptote. Okay, so at x equals to 0 gives us that this y-axis is our vertical asymptote, and moreover we have a horizontal asymptote too, because we can see that numerator of this function cannot be equal to 0, that is y cannot be equal to 0. So this tells me that this function cannot have a 0 value. Therefore at y equals to 0, at y equals to 0, we have a horizontal asymptote. So these are the two asymptotes we have. The numerator is 1, and it cannot be, the function cannot attain a 0 value because the numerator is 1. Therefore we can say that y cannot be equal to 0. Therefore we have a horizontal asymptote at y equals to 0. So these are the two asymptotes of this given function. Moreover, let me highlight some other few points before sketching the graph. So let me mark this x-axis as our asymptote. So we just extend this with some dotted line. These are the two asymptotes we have. Okay, and moreover if we plug in a positive value at x, we could see that our y values becomes positive. Suppose if we plug in some positive values at x equals to some positive values, we are getting y will give us a positive value. So this tells me that our graph will present itself in the first quadrant. So this is the xy plane where the graph will be located. Moreover, if I plug in a negative value at x equals to, for x, suppose if I place a negative value at x, then y will give us a negative value, and this tells me that the graph will present itself in the third quadrant, so symmetrical about origin. So this somehow tells me that this function will be located in first and third quadrant and symmetrical about origin. Moreover, we could see that the degree of this function, odd degree, x equals to 1, we have if x equals to 1 over x, so the degree of x is 1. We could say that the degree of x is 1, odd degree. So that means this tells us that this is a odd function. Therefore the graph will present itself in the first and third quadrant. Definitely symmetrical about origin. So now we are in a position to tell that where the graph would lie. Okay, now few more points to we should look for few other points before sketching this function. Okay, so we could say that x equals to 0 is not in the domain of the function, as we have seen before that 0 is not included in the domain of the function. So let me check the neighborhood of 0 at 0 positive and at 0 negative, what is happening, where my function is moving. So let us consider the limiting value, or let me consider the limiting values. Okay, at limit x approaches, since 0 is not in the domain of the function, we are considering some positive value, a very small neighborhood of 0 in the positive side, 0 plus, and 1 over x. Now as our x increases without bound, then our function is approaching towards 0. As x is approaching, as x is approaching towards 0 plus, we are saying that our function is increasing without bound, and it is getting up like this. For example, if we consider this point, say this point, at this point our function is going up like this. Okay, so here at 0 plus, suppose this point is 0 plus, and as x approaches 0 plus, our function is increasing without bound. Okay, so it is approaching towards almost plus infinity, and as our x approaching 0, negative of 0, a very small value on the left hand side, suppose here this point, then our function is also increasing, but in the negative side. 1 over x is approaching towards with a negative value, is approaching towards infinity, but in the negative direction like this. Okay, so we are getting some ideas from where the graph will plot. Moreover, if I place in x equals to 1, we could see that we have fx equals to 1. So these are the key points, I would say, key points. Let us consider few key points. Key points. At x equals to 1, we have y equals to 1, and at x equals to minus 1, we have y equals to minus 1. So we mark these key points like this. 1, we have 1. So we mark these points as 1, 1. This is our 1, 1 point. And at x equals to minus 1, we have y equals to -1. So this is our another key point, -1, 1. Now we will see what is happening at x equals to as x approaches without bound. Suppose we have limit, we need to check the limiting values before sketching the graph. As x approaches to +infinity, as x is increasing without bound, our function 1 over x is approaching towards a positive value. Okay, 0 plus. And as x approaches to a negative value, limit x approaches to a negative value towards -infinity, our function 1 over x is approaching towards 0 but with a negative sign, a very small negative number. So we could readily see that these are the end behaviors of the graph. At x equals to infinity, we have this graph like this, and at x equals to -infinity, we have, as x approaches to -infinity, we have this. Here we have this y value over here. Y is approaching towards negative value like this. Okay, so one more point to consider over here is that we have a odd vertical asymptote. We could say that the degree odd multiplicity, that 1 over x has odd degree, so it will have a odd vertical asymptote. Odd vertical asymptotes mean the graph will attend infinity at opposite ends. Odd means opposite. Okay, so now we are in a position to sketch the graph of this function, and this will be, let me erase this y over here. Okay, so let me draw the graph of this function. Okay, it will approach towards x-axis, but it will not touch the x-axis. Okay, let me rub this and draw it again. Some problem while drawing the graph of this, sketching the graph. It seems like as if it is leveling off, but it will not touch the x-axis because this is the asymptote. And this part we have like this. Okay, so a double line. Let me draw this part again. So this is the graph of this function. So before sketching the graph of the function, we need to consider those points. This will give us a better picture of the graph if we consider these points. Thanks for watching.